So far we have discussed about kinematics of flows, and in kinematics of flows what we discuss essentially is what is fluid motion without giving any recognition to what are the forces which are behind this motion. Now obviously when a fluid flow takes place there are various forces which are acting, which is making the flow to occur. The obvious forces can be described or broadly categorized in form of a driving force which drives the flow. It may be one or a number of driving forces and some resistive force which is opposing the flow. Now from your basic knowledge in physics you know that one of the obvious resistive forces is the viscous force, but there are situations when the resistive forces in terms of the viscous effects are not that important, and such cases are called as inviscid flows. So the question is, and it is a very obvious question, that we know that all fluids have non-zero viscosity. So why should we study the dynamics of viscous flows at all? This is the first question that we should address our students. So there are various perspectives to it, and I will give you two perspectives. One is, imagine that there is a very high speed flow taking pass across a solid body. So if the flow is of very high speed, we will later on see that how to quantify that in terms of Reynolds number and so on, but just assume qualitatively that it is very high speed flow, then the effect of the wall will be felt in the flow only for a very thin layer of fluid, which we will later on study formally as a boundary layer. Outside this boundary layer the fluid will not directly feel the effect of the wall, that means the momentum disturbance because of the effect of the wall will not be propagated to that outer layer. So the outer layer will not understand any momentum disturbance because of viscous effects. So although the fluid has viscosity, but the outer layer fluid will be dictated by a law of motion for inviscid flow. So fundamentally when such a situation takes place, we can say that the shear stress, which is one of the manifestations of viscous effect, it is a combined product of two things. One is the viscosity, another is the rate of deformation. So if the rate of deformation is 0 or negligible, then it does not matter whether the fluid has viscosity or not, the net effect is that there is no viscous shear stress. So there are many practical situations where you have a layer of fluid within which viscous effects are important, but there is an outer layer where viscous effects are not important, and we can use therefore the inviscid flow analysis. The advantage with this analysis is that with viscous effect the order of the governing differential equation is second order, and with inviscid flow it becomes a first order equation, until and unless there are external forces which give rise to higher order effects, but normally the velocity, the effect related to velocity gradients are confined only to first order. So there is a whole lot of motivation in studying inviscid flows, and we would start with a very simple exercise of deriving the governing differential equation for inviscid flows, which is the so called Euler's equation of motion. Imagine that there is a control volume like this, with dimensions delta x, delta y, delta z along x, y and z. Now, let us analyze all the forces along x direction. So, one possibility is that we make a control volume and do a control volume analysis. This is what could have been the traditional purpose, but you can also imagine this as a fluid element and write equation of motion for a fluid element. They are two different things. So, when we draw this a box like this, it might represent a control volume, it might represent an element of fluid. In the latter case, it is a control mass. Because we have not yet formally learned how to write conservation equations for control volume, we will not follow a control volume of approach here, but we will try to adapt to a control mass or fluid element based approach. So, we will assume this as a fluid element. What are the forces on this fluid element along different directions? So, let us identify the force along the x direction. If the pressure here is P, then the force on the surface is this one, and then the pressure here is P and the force is this one. So, P plus the expansions in P. Therefore, the resultant force along x. So, we are assuming that pressure is the driving force, but you could also have other body force. For example, you could have electrical force, magnetic force, these kind of forces are there. So, to represent that in a unified manner, let us assume that Bx is the body force per unit mass along the x direction. So, rho Bx into delta x into delta y into delta z, this is the body force along the x direction. So, what we will write is a simple statement of the Newton's second law for the fluid element. So, we will write resultant force along x is equal to the mass of the fluid element times the acceleration along x. So, resultant force along x, if you make a balance of this becomes is equal to mass times the acceleration along x. So, and there are higher order terms here. If you take now the limit as delta x, delta y, delta z tend to 0, which we eventually intend to take because we want to derive a differential equation of motion. So, when we derive the differential equation of motion, we shrink the volume to a point, that makes all these things tending to 0. So, you have rho a x in terms of Eulerian variables. If you write Ax, see you Ax is acceleration, this you can write in terms of Lagrangian variable, Eulerian variable, whatever. So, if you write it in terms of the Eulerian variables, then this becomes okay. So, what it essentially means is that your equation of motion along x direction, which we call loosely x momentum, we can write it in a vector form. So, this so called convective component of acceleration we can write as this one, right. So, dot product of the velocity vector with nabla with multiplied operated on u. So, this becomes this is sorry Bx. So, this is the Euler equation of motion along the x direction. Rho is there, right. So, this is the x momentum or Euler's equation along x. Similarly, you have y momentum, and then z momentum. So, what we will do is we will multiply this with the unit vector along x, multiply this with the unit vector along y, and multiply this with the unit vector along z and add, so that we can get an equation which is solely written in terms of the velocity vector. The advantage in writing that form is that when we write a vector form, unlike this form which becomes coordinate system dependent, that form will become coordinate system independent. So, you can write this vector form for some special cases. So, if you do that, then you will get rho This is the Euler equation in vector form. Now we can simplify it further by noting a very important vector identity. Okay. So, this is a well known vector identity, this you can get from any book in vector calculus, very standard vector identity. So, see, this is the abstractness of mathematics translated into the physical field of physics. So, this is like an acceleration, and this you can see that v dot v will be v square, and v square by 2 represents the kinetic energy. So, acceleration is related to a combination of kinetic energy and curl of vorticity and the cross product of velocity with vorticity. So, now what we will do is we will substitute this here so that we can write so first we will write the unsteady term, maybe rho this is rho will be there. Okay. So far so good, but these equations contains vector derivatives, and then engineers want equations where the equation is expressed in terms of simple scalars, and maybe so nice if further the scalars are expressed in algebraic form rather than forms involving derivatives or integrals. Such a form can readily be obtained after we do a couple of steps. One is we take a dot product of this with a line element in the flow field dl, any arbitrary line element in the flow field dl, this vector from one point to another point, a differential vector. So, what we will do is we will take a dot product of this with dl. So, remember the previous thing was a null vector, not really 0 because it is a vector, and we will make a dot of that with dl, and of course that will be 0. We will not consider the unsteady term to begin with because we will have separate treatment for that. So, we will consider the second term and the third term with their dot product with dl. So, So, this becomes del p del x into dx plus del p del y into dy plus del p del z into dz. Okay. So, this is equal to dp, and then in a very similar manner this will be d of v square by 2. Just here replace p with v square by 2, it will become d of v square by 2. So, we are left with the following equation. So, maybe we can divide by rho all the terms. This curl of the velocity is the vorticity vector. Okay. Now, this body force can be anything. So, this equation is valid for any inviscid flow, right. Now, this body force can be anything, right. So, we can imagine the body force to be a force which is what, maybe due to gravity as an example. So, if we take body force due to gravity as an example, and let us say this z axis is positive and upwards and acceleration due to gravity is downwards, then B in this example, in this specific example, B is equal to minus g k. Yes, dot with dl, yes, right. Right. So, if we make a dot of this with dl, so dl is dxi plus dyj plus dzk, so it will become g into dz, this minus and this minus will be absorbed together. So, it will be what are the assumptions behind this equation? Inviscid flow and gravity the only body force which is acting along the negative z direction. In addition to this there is no assumption. So, this is the so called Euler's equation of motion, but represented in a different way. This is also Euler's equation of motion, the representation is just different. Now, the second most important assumption if we make is that say rho is constant. Then we can club all these things together and we also assume that G does not vary with Z. So, if that be the case, then you have d of p by rho plus v square by 2 plus gz Next we assume, see we are going on making assumptions one after the other, and from your prior experience you can understand that eventually with a series of assumptions starting with the Euler equation we are trying to reach the Bernoulli's equation. But it is very important that we understand this systematic way of looking into the assumptions that is getting or taking us towards the final form. So, next we assume steady flow. So, clearly for steady flow okay. So, we have steady flow, then so this term is gone. To get d of this equal to constant, we must have this term also gone. So, what are the cases in which this term will not be there? So, this essentially can be written in terms of a determinant where the 3 rows are the components of V, component of omega and component of dl. So, like let me write u v w. So, this term omega x, omega y, omega z and dx, dy, dz. So, when is this 0? So, one clear case is that the first row and third row, they are, one is the scalar multiplier of the other, and that is possible if you have dx by u equal to dy by v is equal to dz by w. This is one possibility, and this essentially means that dl is a streamline or dl is directed along a streamline, that is the right way to call it. But there are other interesting cases. The second is the vorticity is a null vector, that means irrotational flow. If it is so, it does not matter what is the direction of dl, that means you can integrate this equation along any direction dl between any 2 points 1 and 2, but if you want this to be satisfied, your direction is constrained by the direction of the streamline, that you cannot alter. There are third possibilities, that for example you could have these also one scalar multiplier of the other. So, u by omega x is equal to v by omega y is equal to w by omega z, but that is something which is very unlikely, that is the velocity and vorticity are aligned in the same direction. A more likely condition is something where you choose this dl in such a way that V cross of course the possibility that these are scalar multipliers is also there, but you know that is something, it is coincidental, but this is not coincidental because this depends on your choice of DL. So with all these, so either of these, not all of these together, if either of these is satisfied then this becomes 0, then you are left with d of p by rho plus v square by 2 plus gz is equal to 0. That means you have p by rho plus v square by 2 plus gz is equal to constant. If dl is along a streamline, then this constant has to be evaluated for a particular streamline. If dl is not along a streamline but conditions 2 or 3 are satisfied, then this is a global constant. That means you can write p1 by rho plus v1 square by 2 plus gz1 is equal to p2 by rho plus v2 square by 2 plus gz2, where 1 and 2 are any 2 points. But if dl is constrained to be located on a streamline, then 1 and 2 should be located on that same streamline. So you have to clearly see where from this originates. I believe this derivation is very important, because without this derivation we actually prompt our students to memorize the assumptions of the Bernoulli's equation without keeping in mind where from these assumptions originate. But if we are very clear that this is the reason why these assumptions originate, then the students will be in a position to write the assumptions on their own by looking into the fundamental derivation, and that I think is an essential objective of learning this derivation. Thank you very much. We will continue in the next lecture.